Um, okay, so we've been talking about partial derivatives. And the thing about partial derivatives is they're just that, they're partial. You know, like this, that's the partial derivative of f with respect to x. In other words, y is fixed. All right, we're not changing y at all. We're fixing the y if we're talking about a two variable function. And then the same can be said for, flip can be said for that. That's the partial of f with respect to y. And so x is fixed. In other words, we're just basically calculating a derivative in one direction. Is one way we could put it. And so what our goal here today is figure out a way where we can maybe come up with a way to do a derivative where both the x and the y may be changing and at different rates. Well, before we do that, that's where we're going to utilize what's known as the gradient vector, which basically it's a vector that combines these two partial derivatives. So the gradient vector and the notation for it is the it's the upside down delta symbol is what that symbol is. You know, delta is just a triangle, but the symbol here is the upside down symbol there. It's sometimes referred to as, it's the gradient, this is the gradient vector, but sometimes you'll see it just grade f, or sometimes it's also called del f, del f. Just some notation or things to be aware of there. But like I said, what it is a vector. And so we're back to vectors a little bit here. And what it is, so we take the partial of f with respect to x. And you know, it's evaluated, of course, at x, y. And then the second part of the vector, the j part of the vector, if you will, is the partial with respect to y. So this is the gradient vector of f to variable function f. That's what this describes. And like I said, all it is just making a vector using the partial derivative with respect to x, and then the second part is just the other component, is just the partial f with respect to y. And then of course we can write that you know, using our other notation, like the kind of the Leibniz notation there. And then the ij vector notation, just another way we can write it. Remind you of that. Okay. But that's how you get it. All right, so say we've got f of xy equals ln of x squared plus y squared. And so let's compute the gradient vector of f at 1, 2, or del f at 1, 2. Figure out what that is. So of course the first thing you would do is just, first of all, get the gradient of f. And so that, again, is just the partial. If we shrink it down, leave off the xy part, because that's what's that going to be here? Well, the partial of f with respect to x there, all right, so we've got a little chain rule. The ln, so you do the 1 over thing there, right? And then the derivative of the inside, well, we're doing it with respect to x for the first part, so it would just be 2x. And then the second component is just the partial with respect to y, so it would be 1 over, squared there, 1 over x squared plus y squared. And then same thing, except we're doing it with respect to y, so it would be 2y, would be the other part of that one. Yeah, so the gradient of f at 1, 2, now just plug in x is 1, y is 2, so what would that be? Let's go ahead and put the 2x on top there, so it'd be 2 over x is 1, y is 2, so it'd be 2 over 5. And this would be 2y, so 2 times y would be 4, 1 squared plus, yeah, 5. So it's, it's what it is, all right. That's another thing to compute, gradient. All right, so like I said, what one place we'll use that is doing derivatives and allowing, not just fixing one of the variables and just doing the derivative with respect to the other one, but allowing for the x and the y both to be changing. So, you know, these partials, they're fixed in one direction, the other is changing, but so what this is known as the directional derivative. And what this does is this again allows us to have both have the x changing and the y changing simultaneously in a two-variable system. Okay, and like I said, we'll be given. All right, so we'll be given that the direction that that we want. For example, if we have, say, I want the directional derivative, and I want it in the direction of. So I want the derivative in direction of v equals 2, 1. Well, what basically that means is, all right, so I'm changing my x component here is 2, and so my x is changing 2 for every 1 of y. See what I'm doing there? So x is, so that's giving me a direction, right? X is changing 2, the y is changing 1, so that's telling me which direction to go for this derivative. X is changing 2 units for every 1 unit in y or something like that. So you see what we're doing? We're giving it a direction. Instead of just going specifically in the x direction or specifically in the y direction, now we can go in a different direction, whatever direction we want. Hence it's called directional derivative. Now, for consistency, this direction, all right, so that may be the direction, but for consistency, for one reason is consistency, we're going to use a unit vector for the direction. Which that, that's not hard to get, right? Like here, if I wanted to change that to a unit vector, all you have to do is divide by both parts by the magnitude, right? The unit vector associated with this would be the 2, 1, and then divide that by the magnitude of V. You know what I'm saying? So 2/5 or square root of 5, sorry. And so that would unitize it. So it's not hard. If you got the direction you want, it's not hard to make it a unit vector. So that is one thing that they have us do, is use a unit vector for direction. And so, and again, U for unit vector, and then AB will be the letters used for that unit vector. I'm not sure. Have we used that before for AB? I don't know if we used AB for the unit vector before, but that's what we're going to use here. Okay. All right. So, kind of understand that. Here is then what is called the direction, the derivative of f of x, y, two-variable function, in the direction of u equals ab, where again u is a unit vector. It's this. All right, so we're going to use the big D for derivative, and then the direction is u, so we're going to put the little subscript there for u of f, and then of course two variables, so x, y. All right, so that's equal to, turns out, the easiest way to remember what it is, probably, is that it's the dot product. We're going to do the dot product of something, and it's going to be the gradient of f dotted with our unit vector. So that's the so-called directional derivative formula equation. So it's a dot product. And you're going to use the gradient of f. That's, like I said, this is one use for that gradient vector. Now, some other, of course, ways that could be. So we know that this is the gradient of f. Well, that's just this vector, right? It's just the vector where we put the partial derivatives as the components. And then, of course, u, like I said, we're going to use AB as its components. So when we get to the nitty-gritty, I guess you might say, that's what we're just going to be dotting those two vectors. And then also we could go ahead and remember here on the dot product. All right, so the dot product, what do? Well, you just multiply the component parts. So it'd be the partial of f with respect to x times the a part over here, plus then the partial of f with respect to y times b. So I guess that's really the nitty-gritty of it. That's what the dot product is. Just multiply the components and then add those together. So it is just going to be a number if you have a specific x and y in mind. It's a dot product. Just like any derivative you get, it's a rate of change. So it's just a number usually. So that's what it is, and they prove it. It can be proven with the definition of derivative. So yeah, that's what it is. Okay. Like I said, this is probably the easiest way to remember it. Okay. All right, so let's find the derivative of f of x, y equals x squared plus xy at the point P1, comma 2 in the direction of u, and u equals 1 over square root of 2I plus 1 over square root of 2j. So this one's already got it where the direction we want the derivative, it's already a unit vector, so we don't have to worry about that. So to compute this derivative in that direction, yeah, we've got to, first of all, we got to come up with the gradient. Again, the gradient of f is just the vector with partial of f with respect to y, and the partial with respect to x, and then the partial of f with respect to y is the components. So what do we have here for that? Partial of f with respect to x would be 2x plus y. That would be the partial of f with respect to x of that thing. And then the partial of f with respect to y, well, that's a constant. So that's 0 derivative. And then the derivative of that with respect to y would just be x. Does that sound okay? So this directional derivative in the direction of u yeah, we just do the gradient dotted with u. So in this case, we'd have 2x plus y, comma x, dot that with 1 over square root of 2, comma 1 over square root of 2. And it's probably, instead of multiplying them out, it's probably, since I wanted to add 1, 2, it's probably easiest just to go ahead and plug those in and then dot them, you know what I'm saying? So x is 1, y is 2, so that'd be 4. And x is 1, so it'd be 4, 1, dot that with the 1 over square root of 2. You can do either way you want to. Do the dot product, then plug in the numbers, or plug in the numbers, then do the dot product. Same, I guess, but yeah, so you do 4 times the 1 over square root of 2 plus then the 1 times 1 over square root of 2. Dot product is very simple computation. So what does that wind up being? 4 over square root of 2 plus 1 over square root of 2, so that's the common denominator. Combine those. So this particular value would be 5 over square root of 2. Not bad. Not too bad. Now, good news, I guess. If the thing is, we can extend this. All right, so this was for a 2-variable setup. It can be extended to 3-variable, and the gradient specifically here. So let's say we've got a 3-variable function. The gradient of that, well, it is like you would hope. The gradient of f then would be a 3-component vector, and each component would be the partial derivative with respect to x, and then y and then z. All right, so let's do this one. So let's find derivative of f x, y, z, of x, y, z, and that's going to equal x cubed minus xy squared minus z at 110 in the direction of v equal 2I minus 3j plus 6k. All right. So again, we're looking for a directional derivative, and the directional derivative is, like we've already said, it's the gradient of f, dot that with the unit vector u. So the gradient vector here is, well, it's the partial derivatives as components. And so that's going to be partial of f with respect to x, 3x squared minus y squared, and then z doesn't have an x, so that's the partial of f with respect to x. Partial of f with respect to y minus 2xy, and then the partial of f with respect to z would just be -1. Believe that? Is that okay? With me on that? All right, now, this directional derivative of f, like we said, is the gradient of f dotted with unit vector u. Problem I have here is this a unit vector? Well, the obvious giveaway is it's not called u. Yeah, this is not a unit vector. It's not one unit long, but that's easy to fix. All you have to do to get unit vector u is just to take the v and divide it by its magnitude, and that'll make it a 1 unit long vector. So we take this, how are we going to write it? Since this one's going to be in that form, let's put it back in this form. So we take the 2, -3, 6, and then divide it by magnitude of u, which would be what? 4 plus 9 plus 36. You just take the components, square them, add them together, and then square root all that. Oh, picked nicely there, didn't it? That is square root of 49. Is it not? 49, yeah. So it's 2 sevenths, -3 sevenths, 6 sevenths would be my unit vector components. So let's put it over here. So our directional derivative, gradient of f dot with u, is going to be here. So it'll be the 3x squared minus y squared minus 2xy -1. I'm going to dot that with 2 sevenths. Still looking this over. 2 sevenths, -3 sevenths, 6 sevenths. In this particular case, I want the directional derivative at 110, so the directional derivative of f at 110 is going to turn out to be, all right, so my x is 1, y is 1, so that'd be 3 minus 1, 2, -2, -1. Not that with 2 sevenths. 3 sevenths, 6 sevenths. So what does that give? 4 sevenths, whoops, this is the dot product, so it'd be 4 sevenths plus 6 sevenths plus, minus 6 sevenths. Is that right? 4/7 plus 6/7 minus 6, so it's 4/7. Give it 4. Good?